In this set of reactions stoichiometry, we will be looking at how to calculate the amount of energy released or absorbed in a reaction. Now, like any calculation, there are a number of steps involved. The first one is we need to identify the data. We must have a balanced chemical equation with the amount of energy. So the energy may be of the form change of H, or it could be written into the equation. Now in this case, the known will be what you know. It could be energy, or it could be a mass or a volume. And the unknown can either be the energy or a mass or a volume. Depends on what the question is asking. If the question gives you a mass known or a volume, then you use the mole calculation to find it. And then we use our balanced chemical equation to find the energy released or absorbed. Here's our typical scenario. If you had a volume of gas, you'd find moles known, moles unknown, and then you could find the energy released. If you had a mass known, you'd find moles known, and then you could find the energy released. If you started with energy, you can work out the moles from that and then find what you're looking for. Now let's try an example. It says calculate the energy released when 30 grams of butane gas, so that's our known, undergoes complete combustion. So butane is C4H10, so that's our known, and our unknown in this case is the actual energy. So this is where we're starting. We're starting at a mass known, so we're going to have to use number of moles equals mass over formula mass in order to determine the moles. Remembering that butane is our known and this is our unknown. Let's find the number of moles of butane. So we go the number of moles of C4H10 is equal to a mass over a formula mass. The mass in this case is 30 grams. The formula mass, I'll go to the periodic table and add it up, is 58.12, and this comes out to 0.51617 moles. Now we've got the moles known, we're going to use our balanced chemical equation in order to determine the amount of energy released. Now remember, this is our known and this is our unknown. So you can see here that 2 moles of butane release 5,772 kilojoules of energy. Known, unknown. So when we're calculating our energy, we're going to do it exactly the same way that we did our mole to mole ratio. So that was unknown over known times what we know, the number of moles of C4H10. So in this case, the unknown is 5,772 divided by our known, which is 2, times our moles, which is 0.51617, and this equals 1,489 kilojoules. Or, because there's only 3 significant figures here, 1.49 by 10 to the 3 kilojoules released. Please note there's no such thing as a negative amount of energy. This change of H is, this negative number here tells us it's being released. You shouldn't have a negative amount of energy in your answer. This time we're going to try another problem. We're going to calculate the volume of ethane gas. So this is our unknown at 25 degrees Celsius and 101.3 kilopascals, required to undergo complete combustion to release 10,000 kilojoules of energy. So in this case, Our known is the energy released, and our unknown is the ethane gas. So this time we're starting at energy known so that we can use our equation to find the moles of the unknown. Now remembering, this is our unknown and this is our known. So you can see that 2 moles of ethane released. Now I know it was released because it tells me the change of H is negative. So it released 3,120 kilojoules. This, remember, is our known and this is our unknown. Now what we need to do is we do it the same way we did our mole to mole ratio. The moles of ethane will equal our unknown over our known, but in this case what we know is the energy, which was 10,000 kilojoules. So our unknown is 2, our known is 3,120 times by 10,000, and this will come out to 6.41 moles. Now that we've worked out the energy known and we've worked out the moles of the unknown, we can find the volume of gas. And because it's not at STP, we will be using PV equals nRT. So remember, we've got our moles of our unknown. So now we're just trying to find the volume of the ethane gas at 25 degrees Celsius and 101.3 kilopascals. Now the first thing we must do is always convert our temperature into Kelvin. So the temperature will equal 25 add 273.15, which is 298.15 Kelvin. Now using PV equals nRT. So our pressure is 101.3. We don't know our volume. Our moles is 6.41 times 8.314, which remember I got off my data sheet, times 298.15 Kelvin. Rearranging, the volume was equal to 6.41 times 8.314 times 298.15 divided by 101.3, and this comes out to 157 litres. Now I'd like you to try one for yourself. So go to the OneNote, chemical energy page, energy changes in chemical reactions, and at the bottom of the page you'll find an example. Now once you've tried it, you can check out and see how well you did by going to space, and there is a link to the worked example. Good luck.